In this video, I'm going to be going back into limits. As we start to review for the AP exam in Cal BC, we're going to start from the beginning of the year. We're going to start with that stuff we did at the beginning of the year, these limits, the derivative rules, applications of derivatives, and we'll move into some integrals, some area volume, and then we're going to take a practice AB exam. Okay? Then I'll come back and I'll record a couple of review videos about the C topics. You know, your parametric and polar, your series, whatever else we did. I don't even remember at this point. It's been a whirlwind. All right, so let's start with some limits, right? Let's go back to the very first day of school. All right, so we're going to go back to, you know, kind of just like limits in their most basic form. Right? So we've got the graph of some function f of x pictured here on screen. And they're going to ask you some kind of question like, well, actually, let's start even farther back. Let's start with the pre-cal of this, and we'll talk about what is f of 10. What is f of 10? 6, yes. Okay. But the thing with this is, you know, we're looking at a function with a jump discontinuity. Okay, so we're interested in, let's talk about the limit as x approaches 10 from the negative side. Pleasure. Okay, now usually when I would say from the negative side, I actually give the direction, but from the negative side, which direction is that? Is it left or right? Left, okay. Yes, I'm just reminding you of things you already know. Okay, so the limit from the left is 3. Or it's supposed to be 3. It might be a little less than 3. Okay. If we look at the limit as x approaches 0 from the positive side, that's from the right, the limit of f of x is 6. What would you answer if you were asked about the limit as, oh, whoops, this is supposed to be 10, isn't it? Whoops. Limit as x approaches 10 of f of x. What are we saying here? Fails to exist. Do you remember why we said it failed to exist? Yes, disagreement between one-sided limits. Yes, you were well trained. You were in my pre-cal also. So, you know, we've done this. We've done this a few times. Okay, so we know this. We're good with this. Let's pull in the other case. All right, so here we've got another pretty common type thing. This is a removable discontinuity. I'm going to kind of just ask you the same questions. Okay, g of 10. In this case, what is g of 10? You know what it is. G of 10 is 3, yes. Okay. Then if you look at the limits, the one-sided limits, as x approaches 10, say from the left and from the right, remember, we're basically, the closer we get to 10 from, let's just say from the right, from the positive side. The closer we get to 10, as I'm tracing along here, the closer y is getting to 6. So that's why we say that the limit of g of x as x approaches 10 from the right side is equal to 6. Now I could make the same argument from the left side. The closer you get to 10 from the left side, the closer y gets to 6. Okay. And since these one-sided limits both agree, we can say that the limit as x approaches 10 of g of x is equal to 6. So I'm not going to like copy down the definition of the limit that we took in this class, which is different from the definition of a limit that you will probably take in your next calculus class. And this is what we need to know about the graphs, right? So let's go into some of the ones that are listed algebraically, because those are kind of the more difficult limit questions. All right, the next thing that we used a limit for was really to establish the idea of a derivative. Okay? And there were some multiple choice questions. Now, once we learned Lhopitals Rule, that was kind of like, you know, using a fire hose to put out a candle, but it was. But there were some questions at the beginning before we knew Lhopitals Rule, where we had to, you know, turn this into a derivative, and we could use the power rule, something like that. Okay, so let's just look at some limit that fits this mold. So this is an example of one that is actually just a derivative question disguised as a limit question. Now, yes, we will hit this with Lhopitals Rule in just a couple of minutes, and it'll be better. But it's good to remember that this is the type of question. When you see as h goes to 0, that's a derivative question. That's kind of back to the definition of the derivative, which I might just kind of include off to the right side in pink. Saying that the derivative function is the limit as h approaches 0 of f of x plus h minus f of x divided by h. The limit as run goes towards 0 of rise over run, right? And then the value of the derivative at a particular x value, x equals c, well, we just replace that with c. Okay. Now that is what we're looking at here, this limit in green. Okay. So what is, I'm not seeing a subtraction. So I guess I could just say minus 0. That's really what it is. Okay? So that means that f of c equals 0. F of c plus h is log of 1 plus h. Now, f of c plus h equals log of 1 plus h indicates to me that f is probably log and c is probably 1. But let's make sure this fits, right? Okay, so this is log of 1 plus h. F of c, according to my hypothesis, would be log of 1, which is 0. And then, yes, so this is really what this is. This thing here. This is the derivative of log of x at x equals 1. Okay, so the derivative of log is 1 over x. Let's plug in 1. It should come back 1. Okay, but if we'd seen that log of 1 plus h as h approaches 0 is going to 0 over 0, we could use Lhopitals rule. That'd be 1 over 1 plus h divided by 1. Plug in h equals 0. And you get 1 much faster. Okay. But what if, say on a particular A-B review quiz over limits, you were asked, the limit below represents the derivative of a function f of x at a particular x value, x equals c. Determine f and c. Okay, well, then that all of a sudden would be something Lhopitals rule would not help you. So just be aware of that. Let me do another one, since I've got time. All right, so here we go. We've got 1 cosine of h minus 1 divided by h. Now, this is the type of thing that, if we know what we're doing, it should be really easy. But you could get tricked into maybe thinking it was like sine or something. So you're like, oh, it's a derivative, and this is the derivative of sine. Or maybe you think it's negative sine, because I need to take the derivative of this thing. Either way, I mean, if you're actually trying to find the limit, you should use Lhopitals rule for sure. That's not a catch-all. Maybe I'll show you one where Lhopitals rule won't help you. But it's a catch most. And, okay, so this is the derivative of something at a particular x value. Okay, well, it looks like f is cosine. Okay, so what would c be? Does anybody have an idea of what c would be in this case? Because I'm not seeing it. 0, yeah. Okay. Yes, I'm not seeing it. Yes, thank you over there. As you're taking some sort of late test or whatever. Paying just enough attention to make commentary. All right, so my hypothesis is since f of c plus h equals cosine of h, not to be confused with hyperbolic cosine, that would mean that, f probably cosine x and c equals 0. That's what I think. So let's just make sure that we're subtracting f of c. Cosine of 0. Ah, yes, I know that. That is 1. Okay. So this is the derivative of cosine at x equals 0. So that would be, I think, 0. Yes, because cosine's kind of flat up at the top where it starts. Okay, but that's not what it's going to ask. It's not going to ask you the value of the limit. It's going to ask you for what function is this the derivative of at what point. All right, now I'm going to do some Lhopitals rule questions. Just to remind you of something. And this is really nice. This is probably, I'd say it should be the first thing you think of at this point in the year when we're reviewing the whole year's worth of content. When you go and you look and you see a limit question, that should be the first thing you think. I'm going to do Lhopitals rule on this thing. Because at this point, that's probably the case. And if it's not a Lhopitals rule question, it will quickly become apparent. And, you know, if you do the right thing, it'll become apparent and you'll realize, oh, this is actually an easy question. Or just maybe, if you watch to the end of the video, you'll see this is like one of the hardest Cal 1 questions I've ever seen. Maybe not hardest Cal 1, hardest Cal BC. And now I'm in a binder right now. I'm flipping through. I'm looking for one. I know I've got one that Lhopitals Rule will not help you with. But for now, let's just start with a very straightforward one. So we've got limit as x approaches 0 of sine of x divided by sine of 10x. Okay. Do y'all remember, I know it's been months, but what's your first thing you're supposed to always do when you're faced with a limit is? Yeah, well, just plug it in, really, because occasionally you might just plug it in and find it's not 0, you know, or not 0 divided by 0, or something divided by 0. Always try just plugging it in. Okay. So I'm going to basically say that this is going to sine of 0, which is 0, divided by sine of 0 again, 0 over 0. Okay, it's very important, especially in like a free response context, that if we're evaluating a limit, that we plug it in and show it goes to 0 over 0, or infinity over infinity, because we're going to use Lhopitals Rule. Now remember, the Lhopitals Rule is where we're going to take the derivative of the top and the derivative of the bottom, and we're not going to use the quotient rule. Okay? So the derivative of sine of x is cosine of x. Oh, I'm not sure what that is. My toolbars were showing. And then the derivative of sine of 10x is going to be 10 cosine of 10x. And then we try again and hope that this goes a little better. Okay? So I'm going to plug in x equals 0. And I'm going to have cosine of 0 is 1. That's promising. Divided by 10 times the cosine of 0 is just 10 times 1 is 10. Okay? That is a classical Lhopitals Rule question. Here we've got one by request, special request from 063, for one where repeated Lhopitals Rule was necessary. And I actually think that's probably a good thing for us to do here. Okay, so what we're going to do, this is probably not written the best. This is sine squared theta divided by theta squared. Okay. And we plug in theta equals 0, and sine of 0 is 0, and we square 0, still 0. And then in the denominator, we square 0, and we get 0. Okay? So since it went to Lhopitals Rule, I'm going to need to, since it went to 0 over 0, I need to use Lhopitals Rule. Okay? So I'm going to take the derivative of top and the derivative of bottom. Okay. The derivative of the top, this is sine of theta. You take the sine of theta and then you square it. So I'm going to do the power rule. 2 sine theta cosine theta divided by 2 theta, because I'm just taking the derivative. And this is going to go to 0 over 0. And since it's going to go to 0 over 0, I'm going to apply a trig identity. And I do this one all the time. This is like one of the only trig identities I know. 2 sine theta cosine theta. Anybody know what that is? Yeah, I wouldn't really expect you to. It's sine of 2 theta. Yeah. It's a double angle formula. Oh, this one. I missed the 2 coming down from the power rule. Didn't think about that, I don't think. Okay, so I plug in theta equals 0, and I get sine of 0 over 2 times 0, and it's, oh no, not again. Okay, so use Lhopitals Rule. Okay, so I probably should have said that that's equal to that limit, and then this is going to be equal to the limit as theta goes towards 0. I'm just going to do the same thing again. I'm going to take the derivative of the top. That's 2 cosine of 2 theta. Don't forget the chain rule. Derivative of bottom. And I plug in 0, and I get cosine of 0 is 1. So this is 2 over 2. And that is a valid limit. We're happy. All right. Now here are 2 limits that I want you to try on your own, and make sure you remember these. This was like the most commonly missed thing on the Unit 1 test. So you should definitely try to do these on your own. Think through them. You don't even need, these are relative growth rate questions, right? This is limit as the independent variable goes to infinity. So we're thinking bigger on top, bigger on bottom, essentially are the same. Stuff gets killed off, maybe it doesn't. Think through this, get yourself a hypothesis, check it against mine. If you're watching at home, I'm actually not going to even pause the video because I'm just going to write in the answers. But I am freezing the screen for those of y'all in here. Let y'all think about it for a minute. Alright, so there you go. The first limit is -5 halves because as t goes to infinity, it's infinity on top and bottom. You could use Lhopitals Rule if that was you felt like you needed more. Or you could say, kind of like from pre-cal, relative growth rates, e to the t, they're essentially the same on top and bottom. So you would divide the leading coefficients. That's where you get 5 divided by -2, or -5 halves. But as t goes to negative infinity, remember that, kind of the graph of y equals e to the t looks like this. As t goes to negative infinity, it goes really towards 0. So that means that as t goes to negative infinity, this is 0. And this thing is 0. And so you're just left with 0 plus 1 divided by 3 minus 0. And that's where you get that 1 third. Okay, so I wouldn't want you to forget about those type of limits either. All right, here's another one that we haven't thought about for a while. Like, what would we do if they gave us the function algebraically, but it was a piecewise function? It's like, oh, what's the limit from the left? Okay, you think, okay, as x approaches 3 from the negative side, well, that's where x is less than 3. So what you're going to do is you're going to say, since I'm approaching 3 from the negative side, it's this, and I'm going to use this rule. So this is 1 minus 2 times 3. Which I think is -5. Okay? And then if you're considering what happens as you approach 3 from the positive side, well, x greater than 3 is where you're approaching from the positive side. And you'll use this x squared plus 5. Okay? So this is going to be 3 squared plus 5, and that's 14. Okay, next, I've got another pre-cal question for you. What value of b makes this function continuous? Okay, so you've got piecewise defined function, and we want to make it continuous based on some value of b. So if they're going to be continuous, we need, this piece where x is less than 2, which definitely not going to be a straight line, right, if it's x to the 4th minus 5. We need that thing to meet up with this, kind of wavy thing or whatever. And so they need to share that value. So what we're going to do is we're going to take these two pieces, and we're going to set them equal to each other where x equals 2. So I need x to the 4 minus 5 to equal 3 cosine of pi x plus bx when x equals 2. So you plug in x equals 2. 2 to the 4 is 16, minus 5 is 11. So 3 cosine of 2 pi. Cosine of 2 pi is 1. So that's 3 times 1 plus b times 2. Okay, that means that 8 is equal to 2b, and b is 4. That's a very old question that you may have forgotten about, but it's the type of item that if you saw it on the AP exam in May and you didn't get it right, I'd be really sad for you, Another one you may have forgotten about is you need to be able to sketch the graph of this function. You're able to sketch the graph of y equals the absolute value of x plus 10 divided by x plus 10. Or something similar to that. Right? And the good news is with this function is that is a really easy thing to graph. So what we're going to do is we're just going to mark this off as, say, like this is -10. And maybe this down here is -1, and that's 1. Okay. The absolute value of x divided by x, if you think about it, either x and the absolute value of x are exactly the same or they're exact opposites. So if you divide them, it's either going to be 1 or -1. with y equals the absolute value of x plus 10 divided by x plus 10. You're just going to shift that to the left by 10 units. Think back to algebra 2. Thing is, what happens at x equals negative 10? If you plug in negative 10, you get 0 over 0. 0 over 0 is not a real number, so it doesn't really exist. And then we're just going to draw like that, and we'll draw the rest of the graph like this. One thing I want to mention is that this is the same function as y equals x plus 10 divided by the absolute value of x plus 10, and it really doesn't, oh, whoops, absolute value. It doesn't matter if the absolute value is in the numerator or the denominator. The kind of the mechanism that causes it to be 1 and negative 1 is still exactly the same. So it's not going to change the graph. Now, the last question I've got for you that's based off of a question that showed up in a multiple choice setting. It was one of those, like, I think it used to be number 28 on the multiple choice with no calculator. It was always the hardest question, and it was for the kids that finished the exam really quick, and they needed to have something to think about while they sat there and waited for the section to end. And this one, very tricky. I think something like, I don't remember what it said. It said something, maybe like 80% of BC students missed this one, which means that, 20% of them got it right, meaning it was just replacement level guessing, essentially. And it was based off of this type of situation. So you look at this and you're saying the limit as x approaches 0 of f of 5 plus x squared. It's like, okay, that's kind of like the limit as x is approaching 5 of f of x, which clearly doesn't exist, right? The one-sided limits are not agreeing. But upon closer inspection, if you think about what happens if you put in a small positive number in for x, to 5 plus x squared, you put in a small positive number, it's going to be just a little bit bigger than 5. So you're going to be approaching 5 from the positive side, and it's going to be going towards 3. Right? Now, if you think about doing the same thing with a small negative number, put in a small negative number. When you square it, it's going to become a really small positive number. And so you're still approaching 5 from the right. So this is equal to 3 because 5 plus x squared approaches 5 from the positive side, regardless of if x is positive or negative. And then you can kind of use the same reasoning for this other one. If you look at 5 minus x squared, regardless of if x is positive or negative, from both sides, you're subtracting from 5. And so, as x gets really small, really close to 0, really small positive, really small negative, you're still subtracting it from 5 after you square it. And we're approaching 1 because we're approaching from the negative side. I'm basically saying that 5 minus x squared approaches 5 from the negative side. Right? I could ask you questions like, here, I'll add another one that will definitely be relevant to this discussion. Oh, no. Let's look at the limit as x approaches 0 of f of 5 minus x. Yeah, I think this is perfect to illustrate my point. Okay. If you plug in a small positive number, you're going to have 5 minus, say, 0.1. You'll have 4.9. So you're approaching from the left. And the limit from the left is 1. But if you plug in a small negative number, like say negative 0.01, you're going to be subtracting negative 0.01, and you'll be taking f of 5.01, which is above 5. So then you're approaching from the right. And we can clearly see that the two one-sided limits do not agree. So I say that this limit is the one that does not exist. So I just wanted y'all to be aware of that type of problem, just in case that were to, show up on a quiz or something. And, if you've watched this far, a pretty lengthy video, good for you, and you've definitely seen lots of questions that are going to show up on the quiz next time.